Okay, welcome back to application development in C#. This is the first in the sort of design or coding pattern videos I'm going to do. We're going to talk about three of the really popular design patterns, or coding patterns. The first one is called the Singleton, which we'll do a little bit of a brief introduction to, and then we'll look at some actual code. So, kind of to motivate what you're trying to do here, let's say that you are building an application, and in that application you are trying to manage some really extensive resource. So if we consider this to be some sort of alien database, perhaps, that in order to make a connection to that database, it is going to take you some huge amount of RAM, it's going to take a huge amount of CPU to spin up the connection. So what you don't want to do is you don't want to have 7 or 8 or 9 or 10 or 57 of these things lying around. What you would want to do is limit all of the code in your application or your process to only have access to the one connection. So what this does is it makes sure that you're not going to run out of resources, and basically what you can do is you can plan your resource allocation around only having one of these things available at any given time. So you could certainly do this with a static class that has a static property on it. The problem is the static class part. So static classes cannot be passed as parameters. They can't implement non-static interfaces. They have tons of sort of limitations on them from the inheritance kind of perspective. So it's very limiting if you want to use a static class for this purpose. There's also a bunch of kind of memory management things that get kind of in the way. So static classes are typically not the way this kind of thing happens in production code. So what a singleton does is a singleton essentially expresses a single-use object. So there is a class, and there's only one instantiation or one instance of that class for any given run. And the way that it happens is one of two ways. One, either an eager singleton that immediately creates that instance. So the moment that the code is run and the moment that the resource becomes available, that singleton will create an instance of the object. Or there are lazy singletons. So lazy singletons only create the instance if the instance is used. This is obviously a better situation because if you have a 37 gigabyte alien database connection, you don't necessarily want to use it unless you're gonna actually use it. So you're gonna be able to save the resources in instances where you don't actually have to connect to the database to do anything. So one of the things that is really difficult about the singleton pattern is that it is difficult to make thread safe. And it's not necessarily difficult to make thread safe, it's difficult to remember to make it thread safe. So if you were to go kind of into the wild and you were to look at a whole bunch of production code, you would very likely be able to find a bunch of singletons that exist out in the wild that are not thread safe. And that is not a good situation to be in at all, because one of the major use cases for a singleton is multiple callers being able to access a shared resource at the same time. So going back to our database connection example, for example, if 3 or 4 or 5 or 6 people are trying to get a connection at the same time and your connection is not thread safe, potentially you're going to make multiple copies of the singleton, which is breaking the pattern. You're running up 5 or 6 or 7 copies of this 32 gigabyte of RAM sort of situation, which is not what you want. So there are tons of kind of best practice templates out there, particularly on Stack Overflow, where you can sort of copy and paste it, and a lot of them are wrong, and they're wrong because of this issue with multi-threading, and we'll actually take a look at the most straightforward, sort of naive way of fixing it. In C#, there's also a static way of fixing it with a nested class. And I will put some information about that in the Canvas page. So The components of the pattern. So we talked about how constructors are really just kind of special methods, and the constructor basically just returns an instance of the object that it is, well, constructing. So for a singleton, your constructor obviously needs to be private. And the reason it needs to be private is because you don't want external code creating multiple instances of the singleton. You want the singleton to manage its own instantiation. And the other kind of half of this is that the singleton has to either expose a public method or a property of some kind that actually returns the instance of the class that you care about. And so in C# land, properties make the most sense, and you will see properties almost exclusively used for this purpose in C#. Typically, that property is called current or instance. But you could name it whatever you want. In Java or a Java-like language, typically you have a method called getInstance or something of that general nature, and we'll look at examples of both of those in the code log. So C# is able to do both of these things. In Java, you really are kind of constrained to the method approach, but there's nothing really wrong with that. Properties are basically just glorified methods with a little bit of hidden state in the intermediate language. So before we kind of go to the code, I want to talk a little bit about pitfalls. You might or may not have heard about the concept of a side effect. And I think this is really, really important from an architecture perspective and from kind of a software engineering perspective in general. What a side effect means is, let's say that you pass in some parameters to a method. That method modifies internal state on an object and then does not return that internal state to you or to the caller. What has happened is the caller has made modifications to the object state without actually understanding what it did. And in that case, additional calls, so the second or the third or the fourth or the 900th call to that object could potentially run into unexpected state. You don't necessarily know the state that the previous call let the object in, and that's a really bad situation. And in fact, if you look at Haskell or if you look at F#, a major tenet of those languages is disallowing side effects. Because you will run into situations where you encounter bugs that are created entirely because of the sequence in which a singleton or some other object is accessed. Singleton patterns really open you up to this because their entire point is kind of shared state. And so it's really, really important to make sure that you are not externally modifying internal state on the singleton unless you have a really good reason for doing so. They also have a ton of really kind of common use cases where if you're not extremely sure of what you're doing, and if you haven't done fairly extensive testing on your implementation, bad stuff can happen to you. So I use this word reentrance. What this means is if you have a situation where the same piece of code is run multiple times instead of a single time, you can get into situations where a piece of code can not deadlock itself, but can access its own resources out of order, or you can use something like reflection, which we'll talk about in a subsequent video, to break the pattern maliciously. You can actually use reflection at runtime to generate a new copy of the object, which obviously breaks the entire purpose of having a singleton. So if we go over to the code that I posted on Canvas, I have really 4 singleton class files and then a program file that kind of illustrates a sample run through. So I'm going to start with the simplest one called the eager singleton. What makes this eager? So this is a class, and the class has a static property of itself, of type itself, called current, and it is created immediately once this thing is referenced. So what happens is I have a publicly accessible static property. And this property, the moment that anything happens, will immediately create a brand new eager singleton. So this will happen regardless of if a person actually accesses the getter. Doesn't matter if you try to get the instance or not. The instance is there. It doesn't matter what you say. This is what makes it eager. Outside of that, you can have as many properties, you could have as many methods or functions as you want on the Singleton. Really, the major bang for your buck here is state. So I just have two properties that are kind of just fake kind of placeholder values. But you could play around with this and add methods or whatever you want. The point is that even though the class is not static, your accessibility to the class is in fact static. So what does it mean to be lazy? So here, instead of just immediately creating the instance of the object that is the static property of the same type as the class, what we're going to do is we're going to check to see if current is actually set. So here I have a private backing field called current of type lazy singleton, and external code can't actually access this because it's private. What they have to do is they have to go through the public property. So the public property has no setter, so a person can't provide to me a new implementation of some kind and set the private backing field. The only thing I can do is get access to the private backing field. What will happen is before the private backing field is actually set, the implementation will check to see if it's already set. If it is already set, it will just return to you the set value. If it isn't set yet, it will set it and then return the value. And so literally the only difference between eager singletons and lazy singletons is that the eager singleton always instantiates, the lazy singleton only instantiates if the private backing field is not set. So if you'll remember, maybe 3 or 4 weeks ago, we were kind of making a big deal out of the difference between a field and a property. These are the kinds of coding patterns that make that distinction really, really important. And so that's this is the first kind of time you see the sort of bang for your buck for using properties that isn't necessarily associated with WPF. So here I have exactly the same two sort of public fake testing properties, and then I also have a private constructor that keeps people from going around or circumventing my current property to set their own value or their own local variable to some sort of new instance of lazy singleton. So eager singleton, this thing will certainly do the deed. It's got this problem where if eager singleton, if this has 77,000 properties or a bunch of methods that have absolutely crazy bananas logic in them, they will always be available from the very beginning. Lazy singleton at least prolongs that being brought into memory until it's accessed. And both of these things have a similar problem. And the problem goes something like this. I try to access current at the same time that you try to access current. What will happen is I am given some clock cycles, you are given some clock cycles, and it is typically sort of in this stair-step pattern would be the worst case scenario. So let's say that I get down to the if, and I check the if, and I'm the first person at the if, and it's null. Great. And so I go to line 19, and now I'm waiting. And so let's say that you come behind me and check line 18. I haven't made it to line 20. I haven't actually set the value yet. And you too check the value of current. Lo and behold, it's still null. And so the next clock cycle or the next sort of available clock cycle or time, I will go to this line of code, I will get a new instance of lazy singleton, and you will immediately follow me, and now you're inside of the if, because the if's already fired, and you will get your own version of lazy singleton. So even though this is a private backing field, you have accessed it through a public path, And because I didn't set my backing field prior to you accessing and then setting your own backing field, what has happened is you have overwritten my current implementation. So I got some current value, you came in, overwrote my current value because this thing is static, and now I potentially have done something with that value, potentially in sort of chained dot syntax method calls. And so I'm going to expect some value, but in the middle of me getting that value, you're going to overwrite my current with some new current, and I'm going to get something extremely unexpected. And so unit tests will fail, integration tests will fail, crazy bugs will happen, I'll have no idea why, and I will spend potentially weeks trying to figure out what the heck is going on. That brings us to thread safety. So we have talked in the class kind of tangentially about multi-threaded programming, largely because this is a summer semester and multi-threaded programming is really, really convoluted. It's a complicated concept, has tons of kind of theory around it. If you've taken the operating systems class, you've probably seen a little bit of that in action. So basically there are two ways of living your life. There is the async await pattern that kind of pre-bakes a lot of this stuff for you in terms of C#, but there's also the kind of traditional locking or mutex patterns that you can certainly use inside of C# if you so choose. So the idea is that anything that cannot be run multiple times, so we use the term reentrant, this is not reentrant code, because if you come behind me and run this code the same after I have run the same code, I have this static resource that's shared, and you're going to overwrite my version of that static resource. So this is not reentrant code, and we often call this a critical section. So this critical section needs to have a lock around it so that if I am in this section and you try to come into this section before I leave this section, you will be stranded at line 19. That's literally all lock means. So if we go through the same kind of step-by-step process that we did before, what will happen is my code will get to line 21. I will check to see if there is a current backing field set. If there is not, I will go into the if statement. If you come behind me into line 19, you will be locked and you will stay here until I return my version of current. Once I return my version of current, you will be free to take the lock. So you will take the lock, you will come to line 21, and now you are going to search and see if this is set. And current will be set because I just set it and then returned the value to myself. So what will happen is this if statement will not fire or will not be true for you, and you will get the same instance of the thread safe singleton that I got. So now you're not overwriting me, you are actually getting the same values that I have potentially accidentally set through side effect or through whatever. And so at least at this point with thread safety, there is one and only one version of the truth. And that's really what you want to strive for with a singleton. There is an alternative pattern to this where you can use the concept of a static constructor, and I will put that pattern on the Canvas page kind of as an addendum. It's not super important to get into because this does the deed. This does exactly what you want it to do, and really the difference is the relative laziness of this pattern versus the other pattern. And the kind of sad truth of the matter is relative laziness in terms of large software systems is really a micro optimization most of the time. So this is probably what you're going to see the most of the time. You might see some implementations that use the static constructor, and I kind of want that to be a sort of for your information only kind of thing. So design patterns, the interesting thing about them is they're not necessarily bound to a language. They're largely language agnostic. So you can also find versions of C# singletons that look more like Java singletons, where Java doesn't really have the ability to do this kind of thing with an explicit getter on a property. So what you can do is you can replace that property with a static method. So here, this is doing the exact same lazy implementation. If I find that I don't have my backing field set, I can set the backing field and then return the backing field. And basically this is the Java concept of what a property would be. You don't necessarily have the ability to generate implicit backing fields or anything like that. It's all explicit. It's totally fine. In order to make this thread safe, again, you would just put the lock around the if and the return, and you would have exactly the same syntax as the sort of C# version of the thread safe singleton. So that's kind of the main sort of ideas. You have the eager pattern, which immediately sets the value. You have the lazy pattern that does not immediately set the pattern, even if it's just inside of a method versus inside of a property. And then you also have thread safety, which you can get using the lock keyword. The only thing that maybe we didn't say here is that the lock accepts anything, it accepts some object. And so here what I've done is I've made a private object, and the only purpose for using this object is for the lock. It is also possible to lock based on something like you could even lock on this current backing field. That's kind of a bad idea because the lock, as long as this thing is set, has different behavior than if it's not set, and you can run into deadlocks and all sorts of things, particularly if you try to use a lock for something that you pass into a method. So if you're using an internal or a public or a local variable that's passed in as a parameter, all those things, you could certainly do it. It just is not necessarily great pattern or practice. You typically want a dedicated object to lock around. So that's a thing to think about. So to test this thing, what we want to do, is we want to set up what we would perceive to be two copies of the same singleton. So here I have the lazy singleton, and I'm going to set one memory allocation called first to that singleton. I'm going to set another called second to the same thing, and then what I'm going to do is I'm going to set value 1 on the first one and print value 1 for the second one and show you that this is the value that you're going to get. So what we're showing here is that we have indeed only one copy of the singleton. It doesn't actually matter what variable is pointed to it. These are all just kind of names. And so these are going to be references or pointers to the same underlying object, which is the only object or the only instance of the lazy singleton that you could possibly get. This one is not the thread safe one, so you could potentially run into threading issues, but all of this is synchronous code, so we're not going to. So if we run that thing up, we will run through both versions. So here I have printed second.value1, but I have set first.value1, and you notice 74856 is what I've got up here. If I hit enter, I will have the same behavior for Java style singleton. And so here, this gives you a little bit of flavor of how to call these things. And so here, I'm literally just setting it equal to a parameter or to a property. Here, I actually have to make a method call. So these are very, very similar, but obviously the method call has the parentheses, the property does not. For C#, either or, doesn't really matter. This is usually industry standard. If you have a Java implementation, it's going to look exactly like this. So that's really all I have to say about singletons. There are tons of things to get into if you're interested. There is a whole sort of ideology around how to unit test singletons. They have a lot of use in kind of older web applications, use these things for session management. They're all over the place. So you're very, very likely to see this in industry, and I kind of just wanted you to have a very high level overview of why you might be using them and what they do. So thanks very much for tuning in, and I will see you in the next video.